This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace. Welcome to section 4.9, Rational Functions, Day 1. What is a rational function? Well, anytime you ever see the adjective rational in algebra, it usually means the base word is ratio, which is kind of another way of saying fraction. Look at all these examples. All of these functions are fractions, and that's kind of like the tie-in right here. So we're dealing with functions that have fractions. Here's one of the simpler ones, 1 over x, and that's what it looks like. Let's check out what the domain. We're going to write the domain two different ways. Once using bracket notation and once using interval notation. Set notation, interval notation. Here's the set notation. The domain is all x such that x is not equal to 0, right? Because we have to make sure that we don't get a 0 in the denominator. Using interval notation, we've got this interval here, boom, and then united with this interval here. But making sure that 0 is not included in either interval. Notice the parentheses. Here, same thing. 1 over x squared, we just have to make sure that x is not equal to 0, and that's true for both these intervals. 0 is in neither one of the intervals, and here they are, 1, 2. It looks very similar, and maybe it's a bit steeper than this one right here, and both of them are positive. Because this will never be a negative value. Doesn't even matter if you put negative values into x, when you square them, you get all positive values. This one is rotationally symmetric about the origin, so that means it's an odd function, and this one's an even function because it's symmetric about the y-axis. Here we can see that we've got x minus 3 over x squared plus x minus 2. If you actually factor this, if you factor the denominator, you get x plus 2 and x minus 1. And so then if x were equal to negative 2 or x were equal to positive 1, then you would get a 0 in the denominator. So negative 2 and 1 are the values whereby the function itself is going to be undefined because you'll get a 0 in the denominator. And here they are, negative 2 and 1. They'll create zeros in the denominator. So when you're writing the set notation for the domain, you have to just make sure and specify that x does not equal negative 2 and x does not equal 1, just like that. When you're doing it in interval notation, you can see that we've got 3 separate intervals, and here they are, 1, 2, 3. They're broken up by the 2 different values that we found. So you go from negative infinity to negative 2, and then you don't include negative 2. You don't include negative 2 here either, but you go from negative 2 to 1. You don't include 1, but then you go from 1 to positive infinity. 3 separate intervals for the 3 parts of the graph here when you're talking about the domain. Next, we've got 2x plus 5 over 2x minus 6. So when does this denominator equal 0? When x is equal to 3. So we have to make sure that x is not equal to 3. That's the domain in set notation. All x such that x are not equal to 3. And then here's what that would look like in interval notation. You've got this interval right here from negative infinity to 3, and then don't include 3, but consider the union between this interval and this interval, which is 3 to infinity. Here, in this rational function, we can factor both the numerator and the denominator, and it's worthwhile that we do so in order to figure out what everything is. So when we factor the denominator, we get x squared minus x minus 2. That becomes x minus 2 and x plus 1. So we have to make sure that x is not equal to 2 or x is not equal to negative 1, or else we'll have a 0 in the denominator. And that's how we restrict the domain with set notation. X such that x is not equal to negative 1 and not equal to 2. You can see them on the graph right here. Here's where negative 1 would be, and here's where positive 2 would be. And there are no values on the graph that equal those. You've got this interval here, interval in between, and another interval. The 2 values that create a 0 in the denominator split the whole thing up into 3 different intervals. First interval right here, second interval right here, third interval right here. We got all that by factoring the denominator. You could factor the numerator also if you wanted to, but it would just show you. It would actually show you where the x-intercepts are. It would show you this x-intercept and this x-intercept. F of x is equal to negative x squared over x plus 1. You can just solve the denominator for 0 and just make sure that x doesn't equal negative 1, because if it does, then the function will be undefined. That's x should not equal negative 1. That splits the domain into two different intervals. From negative, this should be a negative infinity up to negative 1, and from negative 1 up to positive infinity. So I want you to do the same thing. I want you to find the domain of f of x equals 1 over x minus 3. It's going to be kind of similar to, say, this one or this one. Just find you don't have to graph it. I just want you to say in set notation and in interval notation what the domains would be. Then, to continue our discussion about domain, what we really find is that these dotted lines have a special name. They're called asymptotes. Say it with me, everybody. Asymptotes. It's a fun word to say. Asymptotes are just lines to which graphs will always get closer. So this graph will always get closer to the dotted line, x equals negative 3. In fact, you can get as close as you want to this dotted line by just getting as far down as you want to on this graph, or getting as far up as you can on this graph. What we can say is that the graph approaches the asymptote. This red graph approaches the asymptote from the left as x approaches 3. This arrow means approaches. And from the right, as x approaches 3 from the right. This is how we say it. You can abbreviate this idea of the graph approaching the value of 3 as x approaches 3 from the right or from the left. Here are basically the 4 different ways that you can say it. You can say f of x approaches infinity as, so the graph approaches positive infinity as x approaches a from the negative side. Notice that this negative sign is kind of like written in the exponent position up top. It's not out front. As x approaches a from the negative side, or from the left. You could say here that the graph of f of x approaches negative infinity. It keeps on going down, 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 as x approaches a from the left-hand side, from the negative side. You could say that f of x approaches positive infinity as x approaches a from the positive side. Or the last combination of these things, you could say that f of x approaches negative infinity as x approaches a from the positive side here. What that looks like, so I've shown you lots of graphs, but here's what that looks like as a numerical table. As x approaches 3, you can see we're starting at 2, then 2.5, then 2.99, then 2.9999, then 2.999999. You're getting closer and closer to 3, and as you do that, you're plugging these numbers into the function. You're substituting them in for x and evaluating them, and you see they get incredibly negative. This is approaching negative infinity because you can get really, really large negative numbers by getting really close to 3. And you can get as close to negative infinity. You can get as large as you want of a negative number by just simply choosing an x value that is as close as you want to 3, or close as you need to 3. Here we're starting at 4. I'm going to approach 3 from the positive side. You can see that the values, that you take these actual values, you plug them into the formula for f. Which one is it? It's this one right here. This is the actual formula for f. If you plug the values in for f into f, then you'll get these incredibly large values here, because it's x minus this and then the reciprocal of it. Anyway, so you plug not 3. If you actually try to plug 3, you get a value that's undefined. You get a 0 in the denominator. But if you do something that's incredibly close to 3 from the positive side, then you'll get an incredibly large positive number. It approaches infinity. So it's really important to know where are the vertical asymptotes. And the way you can do that is you can just figure out where the denominator is going to equal 0, often by factoring. So we got x squared plus 2x minus 8. When is that equal to 0? Well, when x is negative 4 and x is positive 2. You can see they show up on the graph right here. Negative 4 shows up right here. Positive 2 shows up right here. So the answer to the question, where are the asymptotes? The asymptotes are right here at x equals negative 4 and x equals positive 2. One thing that you want to see is that there can be holes in the graph. And holes appear where the function simplifies. So for example, you can factor out an x from both the numerator and the denominator. So here is, this function is exactly equal to this function, but then when you cancel the x's, you have to restrict the result. So here, this is x minus 4 and x squared minus 1, x minus 4, x squared minus 1. But this function is not the same as this function, because here in this function, you can't actually put 0 into x as a value. You'll get a 0 in the denominator, and it'll be undefined. Here, in this simplified version, if you try and plug 0 in, you actually get a value out. Like, it's fine. It's not a big deal. So in order to go from this step to this step, you can say that, yeah, they simplify, but just make sure you don't plug 0 in for x, because if you do, you'll get a 0 in the denominator. It won't be defined. Anyway, let's do, looking at the simplified version, we get x squared minus 1, which, so when you solve that, you get x plus or minus 1. That's where the vertical asymptotes are. Plus 1, minus 1. What happens when x is equal to 0? You get what's actually it's called a hole. And this simplified version is usually much easier to graph than the original. You just have to make sure that you erase this value for x equals 0. It's a hole. You can get as close as you want to the point 0, 4, but as soon as you plug 0 in, you actually don't get any value at all. It's a removable discontinuity. That's what they call it. That's another word for a hole. So you get a hole in the graph there. And those occur where the function simplifies. That would also be true if it was like x minus 4 on the top and x minus 4 on the bottom, and they cancel both x minus 4s. Okay, next example. We have x minus 2 in the numerator, x cubed minus 5x in the denominator. You can figure out where the denominator equals 0 by solving this equation. You can factor out an x, and so that x should not be 0, and x should not be plus or minus the square root of 5. Well, that's where the asymptotes are going to be. We have an asymptote at 0 here. We have an asymptote at positive square root of 5, and an asymptote at negative square root of 5. And that's the whole video. As President Fillmore used to say, start assignment 4I1. Copy the problem list and do the first problem. And I'll see you in class.